The next topic is the elastic collision in one dimension. So we have to prove that the elastic one dimension collision between two bodies, the relative velocity of approach between collision is equal to the relative velocity of separation after the collision. Hence the derived equation for the velocity of the two bodies in terms of their initial velocity before collision. Discuss a special case also. Generally, basically the elastic collision we are discussing about. So we know elastic collision as there is no deformation. So consider two perfect elastic body M1 and M2 moving along the same straight line. So let's say they both are moving along the same straight line like this. Their velocity are u1 and u2. So velocities is u1 and u2. Okay, but the u1 is greater than u2. After some time the two bodies collide. So here you can see that they are colliding. Mhm. The two bodies collide head on, okay, and they continue moving in the same direction. Then after the collision also they continue moving in the same direction, but velocity gets changed. Velocity become v1 and v2 respectively. The two bodies will separately after collision. If v2 is greater than v1, now what happened? Earlier u1 is greater than u2, but now v2 is greater than v1 after the collision. So this is elastic collision, and the assumption is the one dimension. So first thing that we know that elastic collision linear momentum is conserved in any collision. Linear momentum is conserved in all collisions. So first we use this equation m1 u1 m2 u2 is equals to, we know momentum is m mass into velocity. So initial m1 u1 m2 u2 is equals to m1 v1 m2 v2. And what we do, we put this m1 one side and m2 another side. Then we took m1 common, so we got v1 u1 minus v1 and v2 minus u2. Since kinetic energy is also conserved in elastic collision, we know that kinetic energy is also conserved because there is no heat loss or no loss of heat or sound energy. So we can write it like half m1 u1 square plus half m2 v2 square is equals to half m1 v1 square plus half m2 v2 square. Now if we remove this half from both the sides, so we got this equation, and we took m1 one side and m2 m2 another side. Okay. So if we took this m1 one side and m2 one side, then what happened? Okay. So okay. So we took m1 common. So this become m1 like u1 square minus v1 square. So we break like a square minus b square. So we break it like a plus b a minus b. I think you know these things. Then we divide equation 3 and 2. We know this is equation 2 and this is equation 3. If we divide this 2, so we got this u1 plus v1 is equals to u2 plus v2. And if we took u to the one side, u1 minus u2 and v2 minus v1. So the relative velocity of A with respect to B before collision. So this is what this is called as the relative velocity u1 minus u2. So this is the relative velocity of A with respect to B before collision is equals to relative velocity of B with respect to A after the collision. Okay. So relative velocity of A before collision is equals to relative velocity of B after the collision. So we know relative velocity is u1 minus u2 is the relative velocity before collision, and v2 minus v1 is the relative velocity after collision. So, or we can also call this relative velocity before collision, we also call this the relative velocity of approach, because it is approaching towards the second body. Therefore we call it as the approach, and then after collision they get separated. So this called as a relative velocity of separation. Relative means the velocity difference between those two. So thus, in an elastic one-dimensional collision, the relative velocity of approach before collision is equal to the relative velocity of separation after collision. Thus, we prove this statement. Now, velocity of the body after collision from equation 4. So, from equation 4, this equation from, we find the value of v2, and then we put the value of v2 in this in this equation. We find the value of v2 in terms of u2, then we put in this equation. uh, okay, then we put in this equation the momentum conservation. So from here if we solve this, if we solve this, so we can find the value of v1. So this equation will give us the value of v1 by solving this equation. What we do, we just put the value of v2 by this equation. By this equation we put the value of v2 here. Then we put m1 one side, m2 one side. Then we just took v1 common from all the sides, and then just we solve this equation and find the value of v1. So this is the v1. So just we took u1 u2 one side and v1 one side. Then just we divide this m1 plus m2 by this and by this, so we got the v1. Same thing we do with the v1. Okay, so interchanging the subscript 1 and 2 in the above equation. So in place of here we put the value of v2, instead of v2 here we put the value of v1, so that we get find the value of v2. So from here we can easily find the value of v1 and v2. So this as the equation 5 and 6. So this gives the final velocity of the colliding bodies in terms of their initial velocities. Now there are some special cases. So when two bodies of equal mass, so the mass are equal, m1 m2 is equals to m. So don't do anything, just in this equation just equate m1 and m2. So this becomes 0, this becomes 2 times m1. So if you put the value, so you got v1 as 2m u2 by 2m. So you got v1 is equals to u2. Means all the velocity of the second will become the transfer to the v1. So the velocity of mass m2 before collision. Okay. Now if you find the velocity of v2, so v2 become u1. So they get interchange their velocity. Okay. Initially it has velocity u1, it has u2. After collision, what happened? They interchange their velocity. So this is the first one. So this get velocity v2 and this get velocity v1. I mean v2 v1, or this get velocity u2 and this get velocity u1. So that is the case when masses are equal. m1 is equals to m2 is equals to m. Okay, so they just interchange their velocity. Now hence two bodies of equal masses suffer one dimensional elastic collision. Their velocity get exchanged after the collision. Next special case is when a body collides against a stationary body of equal mass. Okay, so let's say a body collides against a stationary. So masses are same. Okay, here masses are same, but there is second body is stationary. Now second body is not in motion, so u2 becomes 0. So if we put the value, this value in velocity, so after collision what happened, this v1 becomes 0. Initially this has velocity u1, this has velocity u2 is equals to 0. After collision what happened, this u1 will become 0, or this u1 will get become v1 and v1 will become 0, and this u1 will equal to the v2. v2 is equals to this u1. This all this velocity that u1 has, that the velocity get transferred to this second particle, and its 0 velocity get transferred to this first particle. So this first particle comes into the rest, and the second particle started moving from the rest with the same velocity at the velocity of this first particle. Elastic body collides against another elastic body of equal mass. Remember, this is for the elastic collision. Initially at the rest, okay, so after the collision, first body comes to rest. So what are the first body? This first body comes into the rest, while second body moves with the initial velocity of the first body. Next special case is when a light body collides against a massive stationary body. So if there is a very small body and there is a massive stationary body, okay, so this body is stationary, massive body is stationary. So what happened, this mass m2 will become very high, m1 will become negligible, and u2 is, u2 is 0, u1 is there some value. So if we put this value over this, so we got this value, this v1 is minus u and v2 will become 0. Okay, so u2 and v2, this remains 0 because this is a very large body. So after colliding, what happened after collision, this again started moving in the backward direction with the same velocity. So this v1 will become negative of the u1. Okay, so it is written, hence when a light body collide against a massive body at rest, so the body rebounds. It rebounds after the collision within the equal and opposite velocity. It rebounds. While the massive body practically remains at the rest. A light ball striking on the wall rebounds almost with the same speed and the wall remain at the rest. Okay, so there is one more case. What happened when a massive body uh, collide against a light stationary body? So what happened if a massive body has a motion and it is colliding? Lighter body is in rest. So then what happened? This m1 is greater and u2 is 0. Here u2 is 0. If we put, so v1 will become u1. So this v1 will become u1 and v2 will become 2 times u1. Okay. So this v1, okay, this body is remain moving with this same velocity. But this velocity started moving with the velocity twice of its initial velocity. Final velocity also remains same. Okay. So hence when a massive body collide against a light body at rest, so the velocity of massive body remain almost unchanged. Okay. No one can change the velocity of this massive body. Even this massive body will move this small body with a twice of its speed, while the lighter body start moving with twice the velocity of the massive body. Okay, it will gain the velocity more than the massive body also after collision. Now next thing is the perfectly inelastic collision. So when the two colliding bodies strike together and moves as a single body after collision, they join and they become a single body with a common velocity after the collision. So after collision, the velocity will become common because they get joined. The collision is perfectly inelastic, perfectly inelastic. So as we see, a body of mass m1 moving with a velocity u1 collides head on. Okay, so m1, u1, m2, m2 is at rest. Okay, okay, another body of m2 at rest. So after the collision, the two bodies move together with a common velocity v. This they are moving with a common velocity, that is the v. After collision, before collision, after collision. Okay, so we know that in elastic collision also linear momentum always remain conserved. So we just use this equation m1 u1 m2 u2 is equals to m1 v1 m2 v2. M1 plus m2 into v. So from here we can find what are the final velocity of this two. So this become m1 by m1 plus m2 into u1. And the we know that in inelastic collision there is a loss in kinetic energy. So we find the loss in kinetic energy by uh, uh, subtracting this initial minus final, or we can say like final minus initial. Okay, because there is a loss, so initial is more and final is less, so therefore we are writing like initial minus final. So we know initially it is half m1 u1 square because u2 is 0, so there is no kinetic energy in second body, it is at rest. Then after what happened, the mass gets joined and velocity become common, so this become this half m1 plus m2 v square. Now what we do, now if we solve this equation, we took if we put the value of v here, this value of v, this equation, let's say, so this equation, the value of v we put here, then we solve this equation. So we got this as a change in kinetic energy as half m1 m2 by m1 plus m2 into u1 square. So as velocity is positive, so this is a positive quantity. Why? Because velocity is positive. So thus the kinetic energy is lost mainly in form of what? Heat and sound energy. Okay. Now if we take the division or ratio of this kinetic energy, so this is final kinetic energy, this is initial kinetic energy. So this becomes the ratio m1 plus m2 by m1 into v square by u1 square. So from here, I think we can from here we can find the value of v square. So this v by u1 will become m1 by m1 plus m2. So from here we got this value m1 by m1 plus m2 square, because we know v is equals to m1 by m1 plus m2 into u from the above equation. So if you put the value here, so we got this. So this is the ratio of final kinetic energy by initial kinetic energy, that is m1 by m1 plus m2. Okay, and this we know this is less than 1, because m1 plus m2 is more than the m1. So this again shows that the kinetic energy final is less than the kinetic energy initial is more than the kinetic energy final, that the kinetic energy after the collision is less than the kinetic energy before the collision. So from these two things we can say that there is a loss in kinetic energy. If the target is massive, let's say this mass m2 is very larger, then what happen? Then if the mass m2 is very larger, then m1 by m2, m1 will become negligible. So m1 by m2 will become approximately, this become very massive quantity, this lower quantity. So therefore this ratio will become approximately 0. So which means final kinetic energy will become 0 if m2 is very large. So what happened? Final kinetic energy will become 0. Hence, when a light moving body collides against a massive body at rest and stick to it, okay, practically all of its kinetic energy is lost. Okay, so when it is when they are attached, so practically what happened? All of their kinetic energy is getting lost. Okay, whatever the kinetic energy initially are there, so the finally the kinetic energy will become 0. Next topic is elastic collision in two dimensions. So earlier we discussed about the one dimension, now we discuss about the two dimension. So discuss elastic collision and what is the glancing collision, then head-on collision, then show that the two identical particles move at a right angle to each other after elastic collision in two dimension. So elastic collision in two dimension, there is no change, just some equation is changing. So suppose a particle of mass m1 moving along the x-axis. So this is a particle m1 and this is moving along the x-axis with a velocity u1. So u1 is its velocity and collide with the another particle of mass m2. This is the mass m2 and is its velocity is 0. Its velocity is 0. So u2 is 0 because it is at the rest and it get collide with this mass. So after collision, okay, let the two particles move with a velocity v1 and v2. So this m1 moves in this direction with a velocity v2, v1, and this m2 move in this direction with a velocity v2. And this makes an angle from this horizontal. This horizontal from this make theta 2, this make theta 1. So here also the angle is same. This angle is theta 2, this angle is theta 1. So from here we can find the component. In the direction of theta, component is cos theta, v2 cos theta. In direction opposite to the angle, it is sin theta. So this also become v1 cos theta 1, v1 sin theta 1. Now what we do, after the collision, the rectangular component of the m1 are okay. So this theta component are along the positive x-axis, m1, this cos theta 1, okay, v1 cos theta 1 and v2 cos theta 2. Here m1 v1 cos theta 1 is along the positive x-axis. Okay. And now this m1 v1 sin theta 1, this is along the positive y-axis. So we are just separating it along that which component is of momentum is along the positive x-axis, because this is a momentum m1 v1 cos theta 1. They are the component of momentum. Now the after collision, the rectangular component of momentum of m2. Initially, we are finding rectangular momentum of m1. So we know momentum is m1 v1, but in the direction, one is in the direction of positive x, one is in the direction of positive y. Now if we talk about the m2, so m2, so one component of m2, that is m2 v2 cos theta, is in the positive x direction, and one component, that is m2 v2 sin theta 2, it is along negative y axis. So applying the principle of conservation of momentum, we know principle of conservation of momentum. So first we are applying in the x direction. So we know in x direction initially velocity is m1 u1. Then there are two velocities. It is m1 u1 cos theta 1 and m2 v2 cos theta 2. So this is also positive x-axis and this is also positive x-axis. So we are equating this. This is initial. They are the final one component. So initial momentum of m1 and m2 along y-axis is 0. Okay. So initial momentum in of m1 and m2, initially there is no momentum in the y-axis. So initially it is 0. And applying the principle of conservation of momentum, so finally this m1 moment v1 sin theta 1 in positive y-axis, and this is in negative axis. So this is the momentum in y direction after collision. Okay. As the kinetic energy is conserved because we are considering the elastic collision, so we can write it like this: half m1 v1 is equals to half m1 v1 plus half m2 v2. So the four unknown quantity v1, here v1 also unknown, v2, theta 1 and theta 2, four unknown quantity cannot be calculated using the three equations. We have only three equations. So by measuring one of the four unknowns, say theta 1 experimentally, the value of other three unknown can be solved. So we have to find the one unknown theta 1, we have to do by experimentally, we have to solve. We have to perform an practical experiment, then we have to find what is the value of theta 2, theta 1, then we have to guess other three values by using these equations. We can't find it by. Now there are some special cases, that is the glancing collision. So glancing collision, like if the theta 1 becomes 0 and theta 2 become 90 degree approximately equal, then if we put the value in the momentum equation, so we got u1 will become v1 and v2 will become 0. If we put the value in equation, and the kinetic energy of the target particles, so half m2 v2 square. So as we know v2 is 0. So the particle which is at the rest initially, so after collision, it's it will remain in rest. Okay, so this v2 will become 0, which means that the after collision also v2 will not move. This and it the velocity of v1 will remain same after collision also. Before collision also it is u1, after collision also it will remain the same, u1. So kinetic energy of the second particle will become 0. Hence in the glancing collision, the incident particle does not lose any kinetic energy. So the incident particle does not lose any kinetic energy because its velocity remains same and is scattered almost undeflected. Okay, so this is scattered almost undeflected. Okay, there is no deflection. Then there is head-on collision. So in such collision, the target particles move in the direction of the incident particle with an angle 0 degree angle. Theta 2 will become 0 here. So then the equation will become like this: m1 v1 then m1 v1 cos theta 1 and m2 v2, because cos 0 will become 1. And the second equation will become like this: 0 is equals to m1 v1 sin theta 1. So equation 3 for the kinetic energy remain unchanged. Okay. So if we look at here, so there is no change in the kinetic energy. Kinetic energy remain unchanged in case of the head-on collision. Next case is the elastic collision of two identical particles. Means the mass is same. So by the conservation of kinetic energy of elastic collision, we know this is the conservation of elastic collision. So if mass is same, so mass got cancelled out. This half and mass got cancelled out. So this become u1 square is equals to v1 square plus v2 square. Then by conservation of linear momentum, so m into u1 is equals to m into v1 plus m into v2 in the vector form. So u1 vector is equals to v1 vector plus v2 vector. Okay, if we cut this m, so this u1 vector will become v1 vector plus v2 vector. So if we do the dot product of u1 vector with u1 vector, so this become like this. If we do dot product u1 vector, if we multiply dot or do dot product u1 vector with the u1 vector, so this become also in the dot product with and come twice. Then if we do the dot product, so v1 v1, then v1 v2, then v2 v1 v2 v1. Okay, so this become 2 v1 v2. Now this become this. Okay, so here the vector will become a scalar. Okay, so now here there is 2 v1 v2. So here it is like v1 and v2. So the v1 vector dot v2 vector is equals to 0. So their dot product will become 0. Okay, so that is a thing that you can learn. Okay, so from here what we do, if we subtract this u1 minus u1, if we send this u1 this side, so this becomes 0. So this becomes 2 v1 vector into v2 vector is equals to 0. From here we get that v1 vector dot v2 vector is equals to 0 by solving this equation. Okay, so this shows that the angle between v1 vector and v2 vector is 90 degree. We know dot product 0 means the angle between them is 90 degree only when the dot product will become 0. So they show that the angle between these two is 90 degree, hence two identical particles move at a right angle to each other after elastic collision in two dimensions. So what happened, they started moving at a right angle to each other, means if the one is moving in x direction, so other is moving in y direction. The angle between them is 90 degree, between their velocity is 90 degree. Okay, next thing is the coefficient of restitution. It is not given in the NCERT, that's for therefore I not cover it, but I provide you in your notes so you can see from your notes. Okay, nothing bigger in that. Okay, so this is the uh, coefficient of restitution that you can see from here. Okay, so this is, then there are different types of collision: elastic, inelastic, perfectly inelastic, and there is one more, that is a super collision. Okay, then the formulas that we use in the collision, first is linear momentum, that is conserved in both elastic and inelastic forces. So this is the equation of linear momentum. Then there is kinetic energy is conserved in only in elastic collision, so we can write like this. Then in one dimension elastic collision, velocity after the collision is given by, so this is the formula for v1 and v2, the final velocity. Then coefficient of restitution for a collision is, so this is the formula for coefficient of restitution. And for a ball rebounding from a floor, its coefficient of restitution will become v by u. For elastic collision, okay, involving no loss in kinetic energy. For this, when there is no loss in kinetic energy, in elastic collision we know no loss in kinetic energy, E become 1. And for inelastic collision involving there is loss of kinetic energy, so E is less than 1. So the unit used, so we measure m1 m2 are in kilogram, velocities are in meter per second, linear momentum in kg meter per second, kinetic energy in joule, coefficient of restitution E has no units.